Hello, my name is Octa Thaib from Aerospace, and today we'll be learning about Johannes Kepler and his second law of planetary motion, which is the law of equal areas. However, before we do that, we will learn a little background info on Johannes Kepler and where the law of equal areas originate from. Johannes Kepler, 1571 to 1630, was a mathematician, astronomer, and astrologer from Germany who was best known for, you guessed it, his laws of planetary motion. In his research book called Astronomia Nova, or A New Astronomy, he analyzed Mars's orbit. Through intense calculations, recalculations, and observations, Kepler realized that Mars, or any other planet's speed, is affected by its distance from the Sun. The farther or closer it is from the Sun, the slower or faster its motion. This contrasted beliefs at the time, which were that planetary orbits is a circle rather than what Kepler discovered, and which we now verify is that planets orbit in an ellipse. This means that the Sun is not at the center, but at a focal point of the elliptical path. This leads into the conceptual definition of the law of equal areas, which states that planets sweep out equal areas in equal times. This is very simple to understand. Here I have a diagram that I drew. As you can see, the Sun is at one of the focal points, and the unnamed planet is located in 4 points. Say it takes the planet 1 month to go from point A to point B. And if we drew lines from the Sun to those points, we would then find the area. Let's say it has an area of 50 units squared. Fast forward in time, and we have the planet traveling from point C to point D. If it takes 1 month to go from C to D, then the triangle formed by the lines has an area of 50 units. The mathematical definition of the law of equal area follows the exact words that was stated. Planets sweep out areas in equal times. It is the area, dA, divided by the time, dt, it took to get from point A to point B. To make life easier, we assume that the area is the area of a triangle, which is 1/2 base times height. The equation now looks like this. dA over dt equals 1/2 base times height over t, which is equal to base times height over 2t. Now you may be wondering what this equation is. It is the aerial velocity, which is defined as the rate of which area is swept by the planets. Since the area and the time of the 2 triangles on the ellipse is constant, the aerial velocity is also constant. In the first example, you can see the forces are labeled. Mars is at the aphelion and is weakly pulled in by the force of the Sun's gravity. This means at this point the velocity is small. At the perihelion, Mars is strongly pulled by the Sun, so its velocity is large. In example 2, you can see you could use the area of a triangle to approximately find the area formed by the lines to the locations of the Moon. The physics problem I made is finding the area of the planet Mars from the aphelion after 7 days. The average orbital speed of Mars is 24 kilometers per second. Using dimensional analysis, I found that the average speed with the unit day is 2,073,600 kilometers per day. Because the problem wants the position of Mars after 7 days, you multiply the number you just got by 7, and you get 14,515,200 kilometers, which is the height. Now to find the area, you plug in the aphelion distance for the base and the height you just found. The area you should get after multiplying by the base height and multiplying by 0.5, you should get 1.808 times 10 to the 15 kilometers squared.